Waves. They're interesting little things. Well, not literal things, really. They're an abstraction, an abstract concept that encompasses countless physical manifestations of the same phenomena. Take some region, for example a vector space, which is described by some value at every point inside it. A wave is the motion of these values, or more accurately, the motion in response to some stimulus. It's like plucking a string, disturbing a system at equilibrium by adding energy, and watching how that disturbance propagates. This can be concrete, a sound wave traveling from a speaker to our ears. Abstract, for example, modeling how expanding the money supply propagates through a network. Or very abstract, like some selected subset that evolves over algorithmic permutations of some field. But right now, I'm not talking about math. I'm talking about physical propagation in space, namely these kind of flawed computer simulations. If you're looking at a periodic source, the energy radiates outward as a function of time. The value of a wave at our point depends on the value of the stimulus when it was emitted. We know the physical locations and distances in space that we're interested in, but we need the amount of time for which it propagated. So we find ourselves the value that relates time to distance, velocity. The speed of sound can be determined for different media, letting us calculate a normalized distance we can use as our propagation function's input instead of time. Now this is great, but also brings up some issues. Well, it's all kind of one big issue, a really big issue. Waves don't always radiate directly outward. Now you might not be able to tell why this looks wrong, and if that doesn't, then this certainly should. It should look like this. See, a wave is the propagation of a stimulus through a medium as a whole. If the characteristics of the medium change, the portion of the wave in the affected region will also change. Take some interface for which, whatever reason, is constituted by a discontinuous change in the wave's propagation velocity. If the wave velocity is higher, that part of the wave will accelerate. If the velocity is slower, the wave in that region will slow down. This causes the wavefront to distort as different portions pass through different substances. Which brings us to the main issue. We simplified our model down to a single dimension in order to simplify the math, then generalized it to higher dimensions by placing that calculation on a ray, a line in 2D or 3D space. So we need to figure out what that line should be. Thankfully, most of the conceptual heavy lifting was done by Fermat in the 1600s. I'm going to dispense with all the nuance and just take his principle at face value. The principle of least time. The ray we need to use is the one which results in the least propagation time. This doesn't mean the shortest distance. Remember, the wave travels at different speeds in different materials. We can take the proposed path and split it into chunks of equal distance, then divide each chunk by its corresponding velocity to find the total propagation time, which you probably recognize as the conceptual basis of an integral. And indeed, there are very elegant ways of describing each scenario using differential equations and then solving for the path analytically. I'm using a computer, so we're going to go with brute force. The method I used bears some resemblance to Newton's method for finding roots, taking a naive initial guess and gradually refining my estimation until I converge on the desired result. In this case, my first guess is a straight line from the selected destination to the emitter's location. It's the base case, and it works pretty well. So what happens when our ray hits an interface and changes direction, either refracting as it passes through or reflecting off of the wall? Well, the mathematical representation for waves uses Snell's law to calculate the exit angle based on the input angle, the velocity in medium 1, and the velocity in medium 2. This phenomena actually falls out from Fermat's principle, which is expected as they're both part of the same model. So I can propagate a ray through different materials and see where it leads. When the ray fails to hit the emitter, I look at how close it came, above or below. I can then make this a new bound for my guess and restart the ray, this time halfway between my initial guess and the other bound, which was initialized to plus or minus pi over 2 of the initial angle when I began. Eventually my guesses converge on the point, Since ray propagation is directionally symmetric, I can use this path to compute the normalized distance and the intensity of the selected point. Now, there are places the stimulus doesn't reach, quote-unquote shadowed regions. In these cases, the bounds converge together without ever reaching the emitter. After trying so many times, the change in the initial angle is too small to produce any meaningful change when propagated, so the output of my algorithm, and it gives up. Now, there are some conceptual issues here, but the main problem is runtime. Just producing this single image took about 15 minutes. Looks cool though. There is another technique I wanted to try. Remember how Snell's law and Fermat's principle emerged from each other? I was mulling over this in my simulations and something called Huygens principle when I had an interesting idea. See, Huygens had a very interesting way of conceptualizing wave propagation. Take a wavefront propagating in some direction. Take each point on that wavefront and radiate out from it spherically. The envelope of all of these circles constitutes the new wavefront. Now, technically, you should do this for every point, but I'm only using an evenly spaced subset as a good enough approximation. I realized you don't actually need most of these circles. You just need the lines from the point on the initial wave to the new wavefront, which happens to be the tangent line at that point. Additionally, these lines end up tracing out the ray path that fell out from Fermat's principle and Snell's law. So, I evenly spaced out a bunch of rays and cast them outward some time step. You can see how the wavefront evolves as I increase the number of rays I'm looking at. All I need to do is write the propagation amplitude out as the wave passes, and a new image is generated. I can incorporate amplitude decay this time, and waves will also self-interfere, which is nice. Still, it's slow. It's faster than the last one, but it's still slow. I tried to throw my previous algorithm into a compute shader with interesting results. I think it slightly broke my graphics card. Yeah. There are more important problems than just slowness, at least more fundamental. See this clear line that's drawn in the shadow? If you think about it, this doesn't make much sense. Water and sound don't do this, so what gives? Well, this is a direct consequence of my approximating Huygens circles with ray segments. I decided to focus on the radiating effects of the stimulus and only the stimulus. But a wave isn't just the response to stimulus, it's the propagation of that energy through some space. The stimulus may be the main contributor, but at any given moment, every point that's not at equilibrium can be considered its own radially radiating stimulus. So I really can't throw out these circles. Sure, they may cancel inside the wavefront, but they propagate outward along edges, smoothing out the clean barriers we saw earlier. A quick aside, you can't actually account for this in the ray model. As a wave packet travels, it actually spreads out, a mathematical side effect of decomposing the stimulus into an infinite sum of steady-state oscillations, each traveling at a slightly different speed or wave velocity or something. Maybe I'll try and account for this. Maybe it's time for me to just move on to the next stage of this project. There is one more technique I want to try, and wasn't able to get to yet. It'll probably include an excess of math, though, and I've kind of been getting into the weeds with that recently. I gotta do something else before this becomes a math, or worse, an educational channel. Not that there's anything wrong with educational channels, it's just I'm not a teacher, and I'm too young to be a professor, I think.